Hello everyone, and welcome to a quick tutorial on how to set up sprites in your own FPGA projects. Recently I made this GitHub repository ECE385 helper tools to help you guys along with your final projects, and I've included step-by-step instructions on how to use some of these tools, but I was still hearing concerns that people weren't able to clearly understand how to actually use the tools or when they would even be useful. So I thought that the best way to resolve these conflicts would be just to make a quick video and explain each of the tools and how to use them. So to get started, we need to clone the GitHub repository. You can do this using two ways. You can either use git shell and do git clone on this website, or you can just download the zip. For those of you that don't have git shell, the easiest way would be just to download the zip and move it into the folder that you want to place it in, and unzip and then use as such. So let's move over to the terminal and see how you actually use the tools. I'm going to be using the terminal since I'm on a Mac, but you guys are probably still going to be using Windows computers, so you're going to need to use CMD. The problems that I have seen with CMD on AWS computers are that if you download and your download is in the U drive and you want to change directory and go to the U drive, some people were having trouble doing that for some reason. AWS is not really allowing that. I'm not sure why. I think the easiest solution for that is to just download and place the downloaded file, the zip file, into the C drive and unzip there. That way you don't have to go through the hassle of switching to the U drive and then trying to work there. So once you have unzipped and have everything ready, change directory into PNG To Hex, and then go into on-chip memory. I'm going to be focusing on on-chip memory in this tutorial because I think that's going to be more important for people. More people are going to be using that. The SRAM version is actually pretty straightforward. It's just a C file. You need to run it and it works, and it's pretty straightforward. If you have any other problems with that, post issues in the GitHub repository and I will address them as such. So now that we are within the on-chip memory folder, I'm just going to do a quick description of the contents and explain which script is used for what and what the internal folders are used for. So there are three internal folders: Sprite Originals, Sprite Converted, and Sprite Bytes. Sprite Originals is where you're going to take your input images that the Python script will then look at and produce the converted PNGs and store them in Sprite Converted. Sprite Bytes is where your outputs will be stored. This is the most important folder in my opinion, because these outputs are what are going to be used in the ram.sv file so that you can actually use your converted data within your projects on the FPGA. So basically, all of these things will work together to help you produce the output that you need so that you can use it within the FPGA. So let's start by looking at PNG to text and PNG3 to text. So I placed these two in the same category because they perform similar tasks. I would use these two only if you have small images or if you have very few images, because what they do is they produce 24-bit values for each of the pixels. Now, this can be okay if you have small images or if you have very few images, because you don't need to compress your images. There's then enough space on the FPGA. I believe there's 3.8 megabits of on-chip memory that you have to use. I might be wrong, but that I think is around the figure that you have. And if you have very few images or if you have small images, you can have the luxury to use 24 bits per pixel. And if you do have that, then these two would be the best files for you to use. The only difference between the two is that PNG to text will produce an output that is 24 bits, and PNG to 3 text will produce an output which is stored in 3 different files. So it'll have an RG and a B file, and you'll have 8 bits per file. So it'll still be 24 bits. It'll just be in 3 different files. So let me run this real quick and let's see what the output looks like. So I'm going to start by running PNG to TXT. I will need to use Python 3 on my Mac, but you guys will use Python when you use CMD in the AWS computers. So let's go ahead and run it. This will prompt you for a file name. Let's go ahead and look at the originals folder and see what we have. So we have a Tetris_I. So we will type Tetris_I and processes the image. Now let's go ahead and look at the converted image. So like I said, this will literally produce the converted file will look exactly like the input file. So there's no difference at all. The important thing here is, and it shouldn't be different, and the important thing here is the Tetris_I.txt file. This file contains R, G, and B values for each pixel in every new line. Now this will then be used by the ram.sv when you do the readmemh, which I'll get to later, because you'll write your .txt file name here, and when you do the readmemh, your RAM block will get initialized with the hex values that are stored in your .txt file. I'll explain that in more detail later. Let's go back and look at what PNG to 3txt does in the meantime. So I'm going to go ahead and run that. It will produce the same prompt. And let's see what the output is. So if we switch out and go to the converted, here's the interesting thing. You might want this specific file if you want to split the RGB and B values into different RAMs and use them separately. And so as you can see, this produced the R channel. This is the green channel of the image, and this is the blue channel. This might or might not be useful. I just have it so that if anyone wants to use it, they can. So those two are only going to be used if you have, as I mentioned earlier, small images. Now, what do you do if you have very large images and a lot of them? This is when these two scripts come along. The palette-based resizer scripts are very important in this case, and I think these are the most interesting ones. So we will also take a look at their code to understand what's happening, and see how they actually work. And we'll do this in the next video. So see you then.